I am presenting my case from seminar. My topic is Film Technology, Measurements and Applications. Welcome to the business. This is my content. I will give brief introduction. We will answer what are thin films. Then we will see how we fabricate thin films, what are the deposition techniques, and after making thin films, how do we measure their properties, what properties do we need to measure, and how we measure, what are the applications of thin films, and challenges and future trends, and then I will conclude my seminar. What are thin films? Thin films are basically thin layer materials, and thickness ranges from few micrometers to some nanometer, and their properties different from their bulk counterparts due to surface to volume ratio and tailored microstructure. Here you can see a comparative diagram. The aluminum foil we use in food wrapping have thickness in few micrometers, and thin films are more thinner than that. You can compare also with atomic and molecular lengths. It is actually between this foil and this molecular lengths films. So main question is how we fabricate thin films. This is not a complete list of all the processes. Mainly it is divided into two types. There are other processes too. First one is chemical vapor deposition, and second one is physical vapor deposition. In chemical vapor deposition, there are many parameters we can vary, and based on that, there are again three types where we can vary pressure and the stimulus used in the reaction. We can also, in the chamber can also vary that. And third one is how we introduce source in chemical vapor chamber. Based on that also we can classify this. Some reactions don't need ultra low pressure, and we can carry out low pressure in somewhat atomic pressure also. Based on this, on varying pressure, there are three types: low pressure CVD, atomic pressure CVD, and ultra high CVD. On the basis of stimulus used, we can again categorize our CVD processes. Like we can use plasma enhanced CVD and photo initiated CVD. Again, on the basis of how sources are introduced, we can use source in sequence to chemical chamber, and based on that there is atomic layer CVD. And then second one is physical vapor deposition. In physical vapor deposition, it is divided into two types, mainly on how we evaporate our source. First one is thermal evaporation. We directly heat it by using joule heating. And second one is sputtering. We bombard it with ions or electrons to heat the source so that it evaporates and get contents on the source, on the substrate. Sorry. I will not give all the IISc all the processes, so I will only discuss about thermal evaporation. The basic principle is we heat the source to make vapor and it deposits on the substrate. This diagram all are familiar with. And this is the chamber where deposition occurs, and there are some vacuum tube, some machines to create vacuum and cooling systems, and some mechanicals and chemicals to determine what pressure is in the chamber. So first process is we need to clean the substrate on which we are going to deposit our film. We need to clean that substrate. Then we need to load our after cleaning, we load our source and substrate inside the chamber. This is the chamber. We load inside this, and after this we create vacuum. It is basically done by roughing followed by vacuum. In roughing, what we do, we first remove all the ball material, ball gas particles. So that after that we use diffusion pump to achieve a low vacuum pressure, and the pressure is typically of the order of 10 or minus 5 millibar, and then we start deposition. Then we heat our source. It is basically double geometry. We provide current and it gets heated, and vapor then travel towards up, and we have substrate placed upside. Then they go towards the substrate and gets condensed there and deposited on the substrate, making thin film. After condensation is done, this film is deposited. Now we have used vacuum machines like diffusion pumps and diffusion pumps, and that is heated up. So to prevent thermal stress, we need to cool that also. So, and after all this, we need to remove that thin film. Actually, we need the pressure inside the chamber is very low, and outside is atmospheric pressure, so we can't directly pull this out. So we need to clean the chamber. After that, we remove our required desired thin film, and yes, we are done. But again, we need to do some roughing for the maintenance of vacuum inside the chamber. Now we are done with our thin film deposition. And next, these are I have listed some advantages and disadvantages of PPT. PPT actually it is done inside the vacuum chamber, so the purity of thin film is high purity, and it is a material versatility. You can apply thin film to, you can use this method to deposit on glass slabs, metals, or even ceramics. So it is of material versatility. You can use it to a wide range of materials. And environmental friendly, it don't produce any harmful chemical gases like CBD, so it is environmental friendly. And the film is of incontinuous, and these are not the CBD or line of size position. Actually, when you deposit, it goes straight up. If there are complex 3D structures, it don't cover everything on the substrate. Second one is high equipment cost and complexity of the process is very complex. You need to monitor the pressures and current. So high skill is required. So, and because it's slightly slow compared to others, and high energy is required. You are using rotary vane pumps, diffusion pumps, coolers, so it consumes high power. We have now aggregated our thin films. Now to use it, we need to know what are its properties. Basically, we need to measure some techniques to measure the properties of thin films. These are the properties we are interested to measure. First, property thickness and surface morphology and roughness. What are the optical properties of the thin film? Then what are electrical properties and mechanical properties and chemical composition of the thin film and its structure. To measure thickness, we have these four methods: ellipsometry, photometry, X-ray reflectivity, and interferometry. In ellipsometry, what happens is that it sends polarized light to sample, and it gets reflected on the plane of distance. There is polarized light, and the polarized angle this layer of distance is P plane and perpendicular to this layer of distance is called S plane. The material sample has a different ability to reflect both S polarized and P plane polarized differently. So when we say here a linear polarized, we get different polarized on this side due to property of this element. And here is a detector, and it measures this change in polarization, and we get idea about its thickness and its optical properties. And this is FTIR, Fourier transform infrared spectroscopy, and this is when this measures optical properties. When light falls, this is being split up. Some motion gets to this fixed mirror and some to this tiny mirror. We can vary this. And here is sample. Light falls in it. Some motion will get transmitted, and detector will detect it. And what happens is that it will give a spectrum. Yeah. Actually, the source will carry evidence and energy process. This will give a spectrum of different intensity and energy, but it is actually difficult to analyze it. So we Fourier transform this to frequency and intensity and get a basic idea about what are the optical properties. And for surface photometer and roughness, we have AFM, atomic force microscopy, and scanning electron microscopy. These are discussed by Daigas. Just for electrical properties, we have 4.0 Hall effect measurement, and mechanical properties is done by this reverse gas based space measurement, chemical composition like X-ray diffraction, and Raman spectroscopy, energy dispersion X-ray spectroscopy. In this 4.0, there are 4 probes, and the distance between the three is same. Here, on the inner two probe, we give potential, and after two probe, we give current, and we measure this, and with some formula we get the resistivity of this material, and the resistivity formula for thin is given by RST, where RS is the resistance per unit area, and is given by pi V by ln 2 into current. After this, we will see what are the applications of thin films. And thin films are used in our day-to-day life, in mobile phone screens, in semiconductor, everywhere we use thin films. We can use thin films in various sectors, energy, healthcare, and in our electronics, everywhere we use thin films. In bionic, what happens? That needs to connect to our neuron, right? To give some visual power to visually impaired persons. That needs to connect to our neuron, but these are some electrodes that need to connect, but that is not biocompatible. So we need to do some thin film coating around that electrode so that it becomes biocompatible to our neuron. We need in our bionic eyes. And protective coating, some thin films like carbon nanotube coating is down to, it is actually hydrophobic. We can make coating of that to get water resistant, and some materials are scratch resistant. We can make thin films to get rid of any scratch. In electronics, we can use thin film to get high conductivity, and we make microprocessors using thin films. it is used in batteries and integrated circuits, and display of monitors is basically thin film. OLED and AMOLED screens we heard of. But we face many challenges in thin film technology. First one is incomplete uniformity. It is very difficult to attain an absolute uniformness on the substrate. And in display technology, even small impurity can damage the image quality and thin films quality. And durability, thin films, the most thinner it is more delicate. So there is always the issue of durability and how much it lasts. So advanced deposition techniques can introduce defects that affect film integrity. And the last one is adhesion. Thin films need to stick properly and tightly for longevity. But it is not possible to actually make desired source and substrate. Suppose we have a substrate, desired substrate, but the required source is not get stick well to it. So these are all the challenges. And fusion plates, more efficient, eco-friendly, and air-driven aviation, and integration of thin film to AI chips, quantum technology, energy storage. In biomedical healthcare, we can use wearable health tech, precise drug delivery, and medical implants. Neuron chip, you may heard about Elon Musk. That he is working for implant inside there. And I am conclusion. Implants are natural in this. They are so thin, ranging from few micrometers to nanometers, and we can fabricate them by PVD and CVD. And by understanding these thin films, we can enhance our efficiency, and our day-to-day life will become simpler. These are my references. Thank you.
Thank you, Surya. Perfect timing. Pretty good.
Here is time already.
So, questions?
So you talk about uniform thickness in the physical vapor deposition.
Alright.
How will you ensure that?
Actually, it is not perfectly uniform. It is PVD is non-conformal. Actually, if the substrate is like this, substrate is like this. You are what do you mean? You are using copper source. Then it comes there from this, here. But it can go here, right? So it is actually what we do, we use CPD. In CPD parameters, we introduce some gas in sourcing gases for. So there are in this chamber in CPD, we give sourcing gases for, and it can go. Move here and there. We use what I call plasma enhanced stimulus. We also use in this case to enhance this uniformity and to get film deposited everywhere.
I have a couple of bit. I think I will speak. You said something which was not quite right in sputter process. You said it will heat the source.
We are using ions or electrons to to get source vapor.
Right. So this is the process of evaporation. So basically heating the source. And these atoms are leaving, group of atoms are leaving the source and the land away. So it's not really a physical temperature going up. It's, because for evaporation to take place, the source has to melt first. This sublimates. So this is one. Second question was the last slide. I think is second last slide. You had something like quantum coding. What is quantum coding?
It is actually in future for this IISc security quantum keys. I'm not read many more about this, but a rough idea to exploit quantum mechanical phenomena and to get increase in.
No, that's okay. No, I think you need to be careful. Like these days, there is a trend of putting quantum in front of everything.
Yes.
Anyway, you need to be careful. So you must have read it somewhere. But, it's not something.
It's only given. It's only given. Download.
Some of the aspects in the machine have some of this. Exactly. Point number 6. I don't think this is correct. This is not correct. When you read it, when you give us analytical context, you should not actually give up their subject.
Nowadays, quantum is.
Because the regime workouts, this gives gases and space to diffuse. And by finding the overall equilibrium, that actually reduces the stress. So to get to the helpful utilities, you will actually heat up the substrate in most cases. There are certain cases and certain types of materials where we cool it down so that the atoms that come in come and get closer directly in the substrate. But those are typically stress frames. So I think it's actually the opposite. Again, it depends on the context of the event.
Is it okay? Yeah, don't buy the shares.
Just a
Quantum antimicrobial coating.
Yes.
এর সাথে কোনো লিঙ্ক নেই ওয়েস্ট করতে গেলে
নামটাও এমন দিয়েছে
কোয়ান্টাম
মনে হচ্ছে একে ভাষার মধ্যে নামটা দিয়েছে
This will reflect polarized light. Polarized plane that is perpendicular to this incidence plane is different, and this is P plane that is along the incidence plane is different for any material. The material that reflects is different for both the types. So you get some elliptical types of polarization from a linear polarized light, and this will be reflected by detector.
This is a birefringent material, then?
Linear polarized light converted into ellipse.
Yes. By reflection, this is occurring. The light will reflected and get into converted into elliptical light.
Due to different power to reflect P plane and S plane.
This is generally true. Is it true for? Because I'm finding it hard to understand myself.
Yes.
Let's say you want to measure the stress, right? So light can only penetrate till the skin. Then beyond that, it doesn't.
We are actually thin, so
আমি কিছু করিনি যেটা তুই ভুল ধরবে
The rotation of the polarization. How does it relate to our measuring sample?
Is that a birefringent material, sir? Is that a sort of birefringence that is occurring? But is that a birefringence material? That reflection? Sorry. Yeah. Okay.
And when you have a thin film, you have to consider the imaginary concept of that. Other two different concepts.
Okay.
The math follows.